This is just to recall what we have discussed in the earlier class. So previously we have discussed the concept of orthogonal diagonalization, which is applicable for symmetric matrix. Because for real symmetric matrix, we have seen that P matrix, P inverse AP equals to T, the diagonal, if this matrix becomes orthogonal. This model matrix, there is a collection of the matrix formed by the eigenvectors of the matrix are actually model matrix. In this case, becomes orthogonal. And then we have seen the quadratic form. Quadratic forms of it is of the kind q of x1, x2. It is a homogeneous polynomial of this form of degree 2, of course, in any number of variables. For example, ax1 x square plus b x1 x2 plus c x1 x2 whole square, and we can write here 2. Then the matrix associated to this quadratic form, matrix of the QF the quadratic form is given by the coefficient of x square, that is a, half of the coefficient of x1 x2, that is b, and then again we have b here and c. Now this matrix, by the definition of this matrix of the quadratic matrix of the quadratic form, is actually always symmetric. Now whenever we have symmetric matrix, so we will be looking at the characteristic of this forms. Okay. Now this quadratic form can be converted into the canonical form. Canonical form, which will have only square forms, also known as sum of squares form. So this will become some a prime x1 square plus some c prime x2 square. So this is what we have discussed in the last class. Now there is another topic that is called definiteness of the quadratic form. So let us define the definiteness of a matrix. For example, if A is an n by n symmetric matrix and X is an n-dimensional vector in the then the matrix A is said to be positive definite if we have X transpose AX equals to greater than 0 for all X greater than X non-zero vectors. If you go back and check that this quadratic form can also be written as X transpose A X. So that is why many textbook will refer X transpose AX is a quadratic form, where A is this matrix and X will be X1 and X2. Of course, if you get X transpose, then you will get X1, X2. So if you just multiply X1, X2, and then A, B, B and C, after that X1, X2, so you are definitely going to get this form. So you will get AX1 square plus 2 Bx1 x2 plus C x2 square. Okay. So we want to study the definiteness of the quadratic form. So that is why first we let us. So you can write this also. This matrix. If the matrix of the quadratic form is positive definite, then we call it a. Then the quadratic form is positive definite. Similarly, it will be called as a positive semi-definite if it has this if it will satisfy this relation. Earlier we had a strictly greater than 0. Now we have greater equals to 0 for all x. Okay. Earlier we had non-zero vector x is a non-zero, but here we are not mentioning that x is a non-zero. Similarly, negative definite will be defined as of this form if it satisfies this relation, and then if it is uh, non-zero vector. Also, we have a negative semi-definite. In that case, we will include less than or equal to 0 for all x. Here also, we do not mention for non-zero. There will be another fifth case, indefinite. Indefinite. If none of the above. Okay. Now, why these are important? Because when, if suppose, as you know that this is a function, quadratic form that we have seen this x1 and x2. Just now we have seen ax1 square plus 2b x1 x2 plus c x2 square. Now, if I say find the maximum value of find the maximum, or let us write minimum. Then we will use the definiteness of the quadratic form. So this will be discussed in when we have to study the concept of uh, calculus. Okay, these concepts will be discussing. We will discuss them in the calculus portion again. So just to for your information. Okay. Now it is very difficult to verify for all the non-zero vectors, because how many non-zero vectors can be found? There are infinite number of choices. But is it possible to verify this relation, that for all the non-zero vectors will try to satisfy this relation? Then only we can tell that this is positive definite matrix. So from this definition, if you want to verify that this matrix, this quadratic form is positive definite or negative definite, it is not an easy task from the definition. So we need a shortcut method. So what is the shortcut method? Okay. So previously we know that the eigenvalue of a matrix, how to find one eigenvalue of a matrix. All the eigenvalues, when all the eigenvalues are positive, strictly greater than 0, then we call it a positive definite matrix. Now if we have all the eigenvalues as negative, less than 0, then we call it a negative definite. Similarly, if we have a situation where some of the eigenvalues, all the eigenvalues are greater or equals to 0, at least one of them is 0, other may be greater than 0, at least one eigenvalue is 0. So this is called a positive semi-definite. Then we may have another case where all the eigenvalues are negative, but at least one should be 0. So this is called a semi-definite, and it will be called indefinite if none of the above case. This is indefinite if none of the above case. That means some are positive, some are negative. Some of them are negative. So this matrix, if you try to find out the eigenvalues, then we can get two eigenvalue are positive, one is negative. So this is indefinite. But if you look at the other matrix, all the eigenvalues are greater than 0, strictly greater than 0. So this is positive definite. This positive definite will, whenever we have positive definite matrix, then when we have a maximization or minimization function, then positive definite matrix will indicate that there is a minimum point. So positive definite will imply minimum, because we know so far in our school mathematics we have seen how to find the maximum and minimum value for single variable case. We don't know how to find the maximum and minimum for multivariable case. If you know, then it is very good. If you don't know, then we'll study in this course. Okay, and then this negative definite will imply maximum. Okay, there will be another relation. So whenever we have minimization, so positive definite will also indicate convex function. Whether this function is convex or not, so negative definite will imply concave function. When we have indefinite, then it will indicate some function which is neither convex nor concave. So these are the properties that are used to study some other important structure of the minimum and maximum. Okay. Now this is also maybe sometimes some tedious job. Okay. There are some other method for which we can define, for which we can find the nature of the quadratic form. So another simple way is there. So of course, those who will study in your seventh semester. Now we are on the first semester, so seventh semester. There is an open elective called optimization technique. Okay, which I also teach optimization techniques. So there, this concept of this positive definite, semi-definite, and negative definite, all these concepts will be used because optimization technique is all about maximization and minimization. So whenever we have maximization, minimization, and the functions are actually multivariable type. So there we have to study of this form. So these concepts will be useful. Maybe some other aspects in your engineering aspects also. Okay. So if we have a matrix of this form, then this matrix is called positive definite if all the determinant, if the determinant of all principal minors are positive. So here we define dk. Dk is the principal minor of order k. So k can start with, for example, 1, 1. It can, if we have consider d2, so this will consider the principal minor and the determinant of the principal minor a11, a12, a21, and a22. So if all the principal minors are actually greater than 0, okay, all are 0, then we say this matrix, or if this matrix is obtained from the quadratic form, then we say the quadratic form is positive definite. But if it is mentioned that whether this matrix is positive definite or not, then we have to find out in this way. So this is another shortcut method to verify whether this is okay. So all the principal, all the determinant of principal minors. Okay, here also you can take 3 by 3, and finally all this. So if you can consider, if you can calculate all these principal minors, then you will get the nature of the quadratic form. Okay. Now similarly, the same concept will be discussed in this way. So if we have for negative definite, so for negative definite, what will be there? The determinant of the principal minors will be as follows. So D1 will be negative. So whenever we have 2 by 2 matrix A, B, B, C, if this is negative, okay, then you can say this is going to be either negative definite or negative semi-definite, or it may be, so this is not going to be. So this type of quick conclusions can be drawn from the looking at the matrix. Okay, then D2, it will be greater than 0. So this the sign of this principal determinants Principal determinant, determinant of the principal minus will be alternate. So first is negative, then is positive, then negative, then positive. And for the nth, if the order is n is odd, then it will be negative. Negative dn will be greater than 0. If it is positive, then negative 1 square will be positive. So dn it will be greater than 0. So in this way, it will proceed. Now, if we have a positive semi-definite matrix, then it will satisfy the first entry, that A11. It should be greater than 0. It should be positive entry. Okay. If it is 0, for example, 0, then we cannot conclude. But all other will be greater or equals to 0. So that we have to look into it. Okay. Similarly, the negative semi-definite can also be defined in this way. So first, D1 should be strictly negative and all other will be alternately. Okay. And indefinite if it is not all the cases. Some of them are positive 0 and negative 0.
Sir,
Yes.
sir, even this would take more time, sir, because if a matrix is some 20 by 20 or
Yeah, that is for there. In this case, you can take the help of computer simulations, computer programs. In fact, hand calculation is difficult if we have a 4 by 4 matrix.
yes, sir.
Okay. This is another alternative way compared to the finding the characteristic values, that means eigenvalues.
Okay.
Okay. But it is much more better way if compared to verifying the definitions. For all non-zero x vector, you have to verify x transpose A x greater than 0. So how many? There are infinite choice. We cannot do this infinite choice. Infinite number of calculation we cannot do.
Yes.
So that is why this will reduce. If not all, then it is at least a better way from the definitions. Now, if you go back and check, if you remember the matrix, let me check this matrix. Let me take this matrix. Okay. So if you try to find out whether this is a positive definite or not. So for this, you have to check what is D1 here. D1 is 3 greater than 0. What is D2? So this is 3 minus 1 minus 1, 5. So this is going to be 15 minus of 1. So this is 14 greater than 0. How about D3? D3 will be this determinant. Take this determinant. 3 minus 1, 1 minus 1, 5 minus 1, 1 minus 1, 3. And this is going to be 36. You can verify. So this is also greater than 0. So all the D quantities, D1, D2 and D3, all are positive. So this is positive definite. In fact, it is for a 3 by 3. I can feel that this is this will take less time than finding the characteristic equations, because here what you have to do, you have to find out the characteristic equation a minus lambda I greater than 0, and then you try to factorize them, and then you simplify, factorize them, and then try to find out the eigenvalues lambda 1, lambda 2, and lambda 3. Okay. But compared to this, for a 3 by 3 matrix, this is an easy task. When it is a 20 by 20 or 100 by 100 matrix, so this is definitely going to be difficult for hand calculation for both cases. Now, for quadratic forms, we will be interested in starting to find out the canonical form. For quadratic form, to find out quadratic form, do some transformation, find out the canonical form. In fact, this transformation is orthogonal transformation, or we can call it a congruent transformation also, because we have seen that this matrix, from this the matrix of the quadratic form, if A is there, then after finding the eigenvectors of this P matrix, the matrix that we'll get P will form the diagonal matrix, and this P will be a orthogonal. So that is why we call it orthogonal transformation. And when we find the canonical form, the canonical form will actually nothing but the sum of the squares, where the coefficients are nothing but this is 1, this is also 1, and this is -2. That means the coefficients are none other than the eigenvalues. So if you can find the eigenvalues, okay, from there you can directly write the canonical form. Okay. If you know the canonical form, you don't have to worry about what is the P matrix, because this D matrix is definitely going to be of this form: 1, 1, -2, given the order you are following. So this is some easy task to verify. For example, if you find the nature of the quadratic form, okay. So if this question is asked to you to find the nature of this quadratic form, then what you will do? First, you have to find the matrix of the QF is given by A. So this D1, you try to find out D1, determinant of the, so this is 1 greater than 0. Similarly, you try to find out D2. So this is 5 minus 1, 4 greater than 0. Similarly, D3, you try to find out. Can you tell me quickly what is D3? Anyone?
Minus 36, sir.
Yes, sir. Negative.
So minus 36.
So negative 36, which is less than 0. So we cannot conclude, right? Indefinite. Okay. Another way, if you try to find out a minus lambda I greater than 0, sorry, equals to 0, then you try to find out the eigenvalues are minus negative 2, others are positive 2. And if you multiply the determinant, you have seen that determinant of A is nothing but the multiplication of lambda 1, lambda 2, and lambda 3. So here also, if you multiply minus 2, 3, and 6. So this is going to be 36. It's less than 0. Yeah. Now this is to find out the definiteness of the quadratic form. There are 6 tasks I have included here. Your task is to verify whether they are positive, definite, indefinite, or other. So try to verify these results, whether these are correct, and also find the corresponding canonical form. Don't forget to find out. So that means if you want to find the canonical form, you have to go through finding the eigenvalues. Otherwise, you cannot say the canonical form. But if the task is only to find the positive definiteness, the definiteness or the nature of the quadratic form, then the finding D1, D2, D3 is sufficient. Okay, these are sufficient for finding the nature of the quadratic form. But if you want to find out the canonical form, you have to find out the eigenvalues. Okay, so try both ways. Okay, so up to this, we have real matrices. The vectors that we have discussed are real vectors, real numbers. The eigenvalues were real numbers. Now, there is a natural question that can it be complex? Yes. The answer is yes. Eigenvalue can be complex number for a complex matrix. But is it possible that we have if we have this matrix, a 2 by 2 matrix, just for your information, we try to find out. That this is a real matrix. This matrix is defined over the real numbers. Okay, so we cannot claim that this is plus minus I are the eigenvalues of the matrix. Because if you try to multiply A, because times lambda times X. Okay, so for real matrix, this, if you try to find out, here it is, I, for example, plus IX, AX. So what is going to be happen? This is going to be, the matrix is going to be complex. So for real matrix, we cannot have, we may get these values from this characteristic equation. But if we have such situation, then we cannot call it a eigenvalues of the real matrix. So that is why we need to extend our knowledge and extend our field. Okay. So this with this notation, we have to proceed further and define what is complex matrices. So up to this we have discussed. So only topic that is remaining is this one, properties of complex matrices. In fact, complex matrices are very, it is a vast chapter, but we have only three type of complex matrices. It is Hermitian matrix, skew Hermitian, and then unitary matrix. So these are very related because we have seen that symmetric matrices has their special natures. So this is symmetric matrix compared to, there is you can say analogous. Okay. Whatever we do in real, for real symmetric, this is skew symmetric. And this is orthogonal. Okay. This is a parallel concept of symmetric matrix is Hermitian. Skew Hermitian is a parallel concept of skew symmetric matrix, and unitary matrix is a parallel concept of this orthogonal matrices. So just to recall that if we have Z, a complex number with the notation I equals to root over minus 1, then the conjugate of this number will be 2 minus 3i. Similarly, the conjugate of this number will be of this form, and the conjugate of real number is nothing but it is itself. Okay. So these are basic concepts to study the properties of complex matrices. So what is a conjugate matrix? Conjugate of a matrix. We have seen the transpose of a matrix. We have seen inverse of a matrix. Now, if we have complex matrices, then there is a new definition is called conjugate matrix, which is nothing but we have to take the conjugate. So if A is a given matrix, then the conjugate of A is denoted by A bar, and this is the elements of will be the conjugate of the matrices of the elements of main A. So that means I comma jth element of A is the complex conjugate of the I comma jth element of A. So for example, if we have this matrix A is 3 plus 4i, this is a complex matrix, 2 minus I, and then 4. Okay. There is nothing much to explain. These are just straightforward. And just take the conjugate. So 3 plus 4i, the conjugate. Take this conjugate. 2 minus I, take the conjugate. 4 conjugate. Conjugate of 4, and so on. So this will indicate. So earlier we have 3 plus 4i. So this will become 3 minus 4i. Here we have 2 minus I. If you take the conjugate, it will become 2 plus I. This is a real number, so it will remain same. Here it is I, so this will be minus I. Here it is 2. Here it is, again it will remain same. So minus 3i, it will become plus 3i. So this is conjugate matrix of A. Given the matrix A, you take the conjugate of each element in the matrix, then the matrix that you obtain is actually conjugate matrix of the given matrix. Okay, a very simple idea. Now there are some small properties. So I have included these properties. So go through it, try to verify if there is any mistakes are there. try to inform me if. So again, these are some simple properties. Go through it and just try to verify. So this is the third property. I would again say, actually here is nothing to explain. If you go through it, you will understand. So that is why, see, your task will be to verify. Whatever is written is correct or not. It is your job to verify. Now there is another concept called transpose of the conjugate matrix. So if we take the transpose, what happens? The rows will be column and columns will be row. But here for complex matrix, it is having a new concept which is called transpose of the conjugate matrix. So that means first we have to take the conjugate and then we have to transpose it. Sometimes it is denoted by a theta, a power, a theta, not to the power. It is just a notation. Okay, a theta, we call it a theta. And the definition is, first we have to take the conjugate and then we transpose it. Okay. So this is just a simple task. For a given matrix A, what we do, we take the transpose, not transpose, first we take the conjugate. Okay, so first we take the conjugate and then you just transpose it. So this column will be the row of the matrix. Similarly, this column will be the row, second row. This third column will be the third row. Okay. So this is a very simple property again. Try to verify. So if the task is to given A, try to find out A conjugate, then try to find out the A theta, and then again you have to find out A theta of theta. So these are very simple tasks. Okay. Now what is Hermitian matrix? With these notations, Hermitian matrix, it is a square matrix. First of all, it is a square matrix. Okay. And the square matrix is said to be Hermitian if the ij element of A will be Aij equals to Aji conjugate. Let me just rephrase this Hermitian matrix. Let us write satisfies. Okay. If this is satisfied for the matrix, then we call it a Hermitian matrix. Okay. So this one example. So 2 and 1. So A 1 2 and then A 2 1. Note that if you take the conjugate, then you will get A21. Okay. So it is like the concept of, if you remember, the symmetric matrix A, B, B, C. First you fix the diagonal element, and the right hand side and the down side, you will have the same elements. Okay. So this is a parallel concept of the symmetric matrix. So that is why what we get this matrix. So you fix this one, and then you have this A12, and A21 will be the conjugate of this element. But we have one more thing. If you take I comma y, that is the diagonal elements, aii equals to aii transpose. That means the diagonal elements will be real numbers because they are satisfying this relation. So that is why the Hermitian matrix will have a real numbers in its principal diagonal are real. All the elements of the are real for Hermitian matrix. Okay. Now there is a theorem. It is known as a matrix A is Hermitian if A equals to A theta. That means take the conjugate and then you take the transpose. Now if you remember, if A equals to A theta, sorry, A transpose, we call it a symmetric matrix for real numbers, for real matrices. So we have said that this is a parallel concept, so that is why A equals to A theta will be there. Okay. So this is an easy verification, you can do it. So there are some other properties which are known as so property 1, 2, 3 and 4. Okay. We will try to prove in the next class. So till then, just go through it and then we will discuss from here the next topics. We'll try to look into the structures of the Hermitian matrix and then other properties. So if you have any doubt, you can ask me.